differences between the two approaches which we have taken so far. In one approach, we started with a relativistic particle and then got the field out of it. But as I keep repeating, when we did that, there were, for example, these loop diagrams which we drew about a particle which is propagating from xi to xi, which very intriguingly led to a bunch of harmonic oscillators, or the 0-point energy of the oscillator. Then we said that let us take the more canonical approach, where you have a scalar field and you quantize the scalar field. You think of the scalar field as a system and you quantize that system. Then you have again a whole bunch of harmonic oscillators, and the vacuum of the original bunch of harmonic oscillators is sort of thought of as the ground state of the system, and the excitations above the vacuum were identified with the particles. So as far as the particles were concerned, we didn't have any problem because the excitations had the correct dispersion relation, their behavior is all fine, etc., etc. We even got a relativistic propagator arising out of it, causality was maintained, everything was fine. All our problems begin with the vacuum state itself. Because in the case of a particle-based approach, you start by saying that, well, if there is a particle, there is a particle, if there is no particle, it is a vacuum. But in the case of a field theoretic approach, when there is no particle, you are at the ground state, which is the ground state of all the oscillators. And that is not a completely trivial state. And as we wrote down the other day, if you write down the wave functional for the field in the ground state, you find that there is a non-zero probability for any field configurations to occur. Now it turns out that this leads to a lot of observable effects, at least two of them which are very important. And one of them is what I mentioned the other day called the Casimir effect, that if I have two plates kept in the laboratory, the electromagnetic vacuum behaves in a strange way and there is a force of attraction between the plates. This we will do after we have done the quantum theory of the electromagnetic field. But this has to do with the modification of the vacuum. So that part I want you to understand so that the connection will be clear. See, when we try to quantize the field, we use the modes e to the I k dot x, the spatial modes, right? These are the running waves and you expand the field in terms of them. That is, you identify the harmonic oscillators by saying that you start with the field phi and you write it as an integral over d3k over q pi the whole cube qk of t e to the I k dot x.
We could easily have taken spherical harmonics as well as.
I'm going to talk about that in a minute. Okay, so you expand it in terms of this e to the I k dot x, and e to the I k dot x is just one complete set of orthonormal functions which I can use in R3. And as Surya was saying, instead of this, we could have expanded it in some YLM theta phi or whatever, and we could have used any other mode functions. Okay. If you use a set of mode functions which cover the entire space and there are no funny boundary conditions, and when you do things rigorously, you work in terms of wave packets so that you assume everything vanishes at infinity, then whether you use different coordinates in space will not create any problem. But if you are talking about a situation where there are two plates, okay, so the situation which one is considering is something where along the x-axis, you say that there is a plate here and there is a plate here, and this is at a distance L. This of course makes sense only in electromagnetism, but just as a mathematical exercise, think of it for a scalar field, where you say that the scalar field vanishes at these 2 points. Now why should the scalar field vanish? It vanishes because it is in some sense interacting with whatever you have given. In the case of electromagnetic field, there are conducting electrons in the metal plates and it is interacting with it. Okay, so we are no longer really speaking dealing with free field theory. You are dealing with a field in an external agency, which in this particular case is in the presence of the metal plates. So once you have got that, the mode functions which you will use here will be sine and phi by s, at least along the x-axis, right? Yeah.
What is that term you're using, mode function?
Mode functions. Oh, okay. By mode functions, I just mean e to the I k dot x. So these are the set of I mean modes in the sense of modes of a wave. So for every k, you have a particular wavelength, and in that wavelength, this is a very standard terminology from essentially study of wave physics. It has nothing to do with quantum physics. These are the modes in this, or the modes of vibration. I mean, if you have anything which you hit and it vibrates, there are modes of vibration of that particular membrane or drum or whatever. These are the modes which satisfy the standard wave equation. Okay, so I'm just using that terminology to refer to this e to the I k dot x. So if you have been putting in boundary conditions here, then along the x-axis you won't use e to the I k dot x because that will not vanish at 0 and L. You will use instead some sign kxx, where kx is n pi over l, so that it has nodes at the 2 points. Now you have changed the rules of the game. If you go back to the original derivation of the vacuum functional, we obtained a result for the vacuum functional where we wrote it down. The vacuum functional for the scalar field, the ground state. We had a result which essentially went as exponential minus some integral over d3x, d3y upon some again 4 pi square. Then we had a gradient of phi evaluated at x dotted with gradient of phi evaluated to y upon x minus y the whole square. You may recall this result. Okay? At one crucial place there, after you have taken the ground state function in terms of mode qk dot square, omega k qk dot square, that is standard, that is independent of what mode functions you are using here. You wanted to write it back in terms of phi. So there I used the Fourier inversion transform in order to get it into this form. If you now do this with these plates, then the inversion will be different and the actual wave functional will be different. Okay, I'm not going to do that because it doesn't lead to anything great, very enlightening other than what I have mentioned. Finally, when you write it down, instead of this, you will have a different kind of kernel, which is multiplying the operator, multiplying the field configuration. Now, if you think for a minute, you will see that it is obvious. If you take this wave functional and you choose a field configuration which does not vanish at these 2 points. Okay, take any of your wave function, any function phi of x which does not vanish here, and you compute it. You get some non-zero number, which means that the probability for a field configuration which does not vanish at the plates is non-zero. But that is precisely what we are banning. We are saying that we are only going to consider those field configurations which vanish on these two. So this cannot be the wave functional in the presence of the plate. Now this is very nice because this immediately tells you that the vacuum state you are talking about are two different creatures. See, the physics has this way of thinking about the ground state as the vacuum state, but the vacuum state clearly depends on what mode functions you are going to use. In the sense that when you write down the wave functional and you ask for the probability amplitude for a particular field configuration, that will be different in the presence of the plate and in the absence of the plate, as it should be. Okay? So any field configuration now has a different probability, which means you have tinkered with the vacuum and it's a different vacuum state. So there is nothing surprising that the energy of that vacuum state will be different, and the difference in the energy between this vacuum state and the original vacuum state is going to be something. It turns out that that is finite and that is what leads to the Casimir wave. Now this we will do, as I said, in great detail when we do electromagnetic field, but I just wanted to point out that this has to do with changing the boundary condition on these mode functions. But there is a lot more intriguing effect, which is usually not discussed in introductory classes, but I think it is fairly elementary and very important, so I want to do that. This has to do with, this is almost some kind of a frontier area in research in the sense that papers are being written even today, which has to do with the fact that the vacuum functional which you have here actually looks like a thermal state for certain class of observers. And this is what underlies this phenomena of temperature for black holes, etc., etc. So I want to spend some time introduce it to you in a very simple context, which has no black holes or any such thing. We will just say that if there is a particular region of space which is not accessible to an observer, which is what happens in some sense in the black hole as well. There is a horizon and there is a region inside the horizon which is not accessible to you. Then, when you are looking at an observable which is built out of things which you can observe, you will have to trace out the unobserved degrees of freedom. This is what we do in statistical mechanics. Whenever you do statistical mechanics from a fundamental point of view, what you are going to say is that ultimately the state of the system is described by giving the position and momentum of every molecule of the gas. But you try to describe it in terms of certain macro states which only has, let us say, the pressure, volume, temperature, a few finite things determined for you. So you are going to sum over all the micro states which are consistent with the macro state, and that is what leads to entropy, temperature and all these things. Okay? Something similar happens here, and I want to derive that result for you. Now before we do that, there is a crucial difference between what I talked about here. There is a similarity and a difference. The similarity is that both comes out because the vacuum fluctuations has a different pattern in two different frames. And here the vacuum fluctuations has a different pattern when the boundary condition is changed, which is same as saying that when you change the observer, you have to change the boundary conditions in some sense. So in that sense, it is similar. And it also has to do with the modification of the mode function. But the difference is that here, the question of time and the vacuum state plays a much more vital role than in the case of cassette. So I wanted to first introduce that. So in order to do that, let us go back to our standard scalar field quantization and the mode expansion, where we wrote phi of x as integral over some d omega k. This is the standard whatever we have been doing so far. And we wrote ak e to the minus ikx plus ak dagger e to the ikx. So what we did, let us get the logic very right. You started with a field operator, you introduce a Hamiltonian, then using the Hamiltonian and the field operator, you went around deciding how the field operator is going to evolve. Then we found that the solutions to the field operators can be expanded in terms of these things. These are the mode functions now. Once you have written down this takes care of itself because it's the Hermitian conjugate. So you started with these mode functions, the coefficient of which you called another operator. Then we found that the commutation rules between phi and pi tells you that this AK AP dagger was some 2 pi the whole cubed 2 omega p derived as a function of p minus k. This is what we found, right? Now, these commutation rules immediately tells you that there is a ground state which is annihilated by A's. So you start with these A's and act on this state and that gives you 0. And the particles are defined as excitations using these creation operator. Now the question is, how unique is this A? Okay. Suppose I have another set of A's which satisfies the same commutation rule, and if I can be expanded in a similar manner, then I can define a new vacuum state. Now, will that new vacuum state be something in which the old particles will be there? That is, suppose I take A dagger A and compute its expectation value in the new vacuum state, will I get a non-zero value? Then I am in trouble, at least so to speak. I am in trouble in the sense that the concept of vacuum and concept of particle now depends on how I have decomposed this mode functions. Now it turns out this is indeed the case, and you need some extra criterion to identify how this states has to be constructed. So that is what I wanted to talk to you about. So
here we can, in terms of the spherical harmonics, we can introduce.
Right. I'm going to just come to that. So first let me tell you one set of things where there is no problem. That corresponds to your spherical harmonics. Suppose I take e to the minus ikx and I combine them. That is, I take e to the minus ikx multiplied by some c of k and add up all the k's. I mean, think of it as discrete for a moment. It is a lot easier that way. Think of each k as a discrete label. Then I am just going to take e to the minus ikx. If once the vector k is specified, its frequency is specified. Okay, then I multiply it by a set of coefficients and just combine them. Then I have no problem because I will have a new combination. So these AKs will be linear combinations of the old AKs. Now, if the original AK was annihilating the vacuum, any linear combinations of AKs will also be annihilating the vacuum. So when you take the plane waves and you expand it in spherical harmonics, that is what happens. Okay, there is no problem. The problem arises if you mix up these two. So let me give you an example. This is an example which we have seen in a different context very early on. But let me write it again and then we will see. Suppose I say that this AK, this is the simplest example you can think of, is some alpha times I need some other variable, I will call it Bk. These are not the Bk's we introduced in complex scalar field. Okay, so it just I'm still talking about real scalar field plus some beta Bk dagger. Okay, and the corresponding expressions for AK dagger. Which is alpha star Bk dagger plus beta star Bk. Now we want AK and AK dagger to satisfy a particular commutation rule and Bk and Bk dagger also to satisfy the same commutation rule. Now you can work it out. I will leave it to you for figuring it out. It's very simple. You can show that if alpha square minus beta square, mod alpha square minus mod beta square is 1, then B is also satisfied the same commutation rules as A. Okay? Now let us go and plug this into this. Then what you will find is that your phi of x now becomes you have integral over d omega k let us write it in a particular way. AK will have an alpha Bk times e to the minus ikx. Then this AK dar will have an alpha beta star Bk. Right? Okay, let me write it and then combine them together. So this is alpha B, I'll suppress K, the label, plus beta B dagger e to the minus ikx plus alpha star B dagger plus beta star B e to the ikx. So this when you add them up, this can be written as integral d omega k. You have B into alpha e to the minus ikx. I want to pick up the B from here plus beta star e to the ikx. And everything else is fixed by Hermitian conjugation plus the Hermitian conjugate. What does this mean? We originally had this expanded as AK e to the minus ikx and its Hermitian conjugate. Now we have it expanded as bk, so now I can reintroduce the k's here. Bk times something, which is not e to the minus ikx, but a linear superposition of the two, plus its Hermitian conjugate. Okay. Suppose I call this some fk, then I have now an expansion which is integral d omega k bk some fk of x, which is stands for this entire expression. This is what I am calling fk of x, plus bk dagger f star k of x. So I have something there and I have something similar here. But the a's and b's are related by this. Now instead of this combination, I could have originally started with these functions as the mode function. I could have expanded phi. Left hand sides are the same. Phi is the phi. Okay? And the commutation rules are all fine. Now I can go ahead and define a vacuum state for bk. So I define a B vacuum as bk, so this I should have more precisely called the A vacuum. So I can define a vacuum state by saying that this implies that I have a new set of vacuum states which are the B vacuum, which is this is equal to. Okay. But now if I calculate the AK dagger AK, suppose I take the B vacuum and I compute A dagger A in the B vacuum. This is the number of A particles in the B vacuum. Of course, number of A particles in A vacuum is trivially 0. But if I do this, I am going to act with A on this object on this. This is not going to contribute. But I will pick up a beta times some one particle state. Similarly, the other thing in the reverse direction. So I will find that this is equal to mod beta square. So now I am in some kind of a paradoxical situation. Originally I defined a vacuum state in which there were no A particles, but I could have done the scalar field theory. I mean, you do it like this, somebody else is saying that I am not going to use e to the minus ikx, I am going to use alpha e to the minus ikx plus beta star e to the plus ikx. These are also the solutions to the Klein-Gordon equation. It will satisfy all the evolutionary criteria and my B's will also satisfy this, and I am going to define my vacuum state, one particle state, etc. out of that. His particles will be different from your particles, because in your vacuum he will find particles and vice versa. So you run into trouble. So you need an extra criterion which we have not at all mentioned so far to decide how you choose these mode functions. Okay? And the criterion we use is that these mode functions should be positive frequency objects with respect to the Hamiltonian which you introduce. That is, roughly speaking, they should go as e to the minus I omega t. There are more formal ways of defining it, but this is good enough. So if they go as e to the minus I omega t, then I d by dt acting on it will give you omega, which is plus omega. So the criterion which we use is that the mode function should go as e to the minus I omega k t. Nothing is said about the spatial part. So in the spatial part, you can have plane waves, you can have, YLM theta phi's, etc. They won't change anything. If you have a plane electromagnetic wave and you think in terms of angular harmonics, then you will still have the same kind of photons which are describing it. But you are not allowed to mix up positive frequency modes with negative frequency modes. These are the negative frequency modes and these are the positive frequency modes. The criterion is used by saying that the Hamiltonian operator, which is your I d by dt, acting on that is going to produce for you a plus omega. It's an eigenfunction with plus omega. Okay. That is violated by this. These things do not satisfy just a positive frequency mode. Now, the beauty is that if you are studying a Lorentz invariant quantum field theory, this is a Lorentz invariant criterion. That is, if I start with a positive frequency mode, if I make a Lorentz transformation, I will still remain within the positive frequency set. This does not ban you from even doing linear combinations of positive frequency modes. So instead of e to the minus I omega kt, suppose I had taken a sum f of omega k and combined them up, e to the minus I omega kt plus e to the minus 3 I omega kt or something. Nothing will go wrong because the particles will still remain the particles because you are only combining all these among themselves. These are like beta equals 0 transformation. Incidentally, I chose a very simple case where the k goes to k. You could have had an alpha here which depends on k, p and the p. That is, you could have mixed up different momentum eigenvalues. The same mathematics will go through, but this is good enough for us. Now, if you go back to our discussion of vacuum to vacuum amplitude, which we did long back, and we had all kinds of confusion in the class about what is an in vacuum and what is an out vacuum. There, the difference between in and out is exactly the same. That is, you start with an in vacuum, and then there is a linear combinations of the A and A dagger gives you the out A and A dagger, and the out the particles are present in the in vacuum. But there we said there is something very physical going on. There is a J of x which is a source which is actually creating the particles. But here that is not what we are talking about. There is no external source. We do not even have things like Casimir plates or anything. We are just talking about a free field theory in full vacuum. You have one set of mode functions and we choose another set of mode functions, and then you have the vacuum becoming different. Okay? In order to avoid this from happening, you impose a condition that we must have positive frequency modes as a choice. Yeah.
I'm not sure what exactly the trouble is, because if the vacuum changes,
Right.
I mean, if we have two different interpretations, won't it be consistent? I mean,
No, because when you say vacuum, you normally mean that your particle excitations do not exist in that. Now, we don't want it to depend on which observer. You want a theory to be Lorentz invariant, so you want a vacuum state to be Lorentz invariant. So you don't want one person to say that I am in a vacuum state and the other person interpreting the same state as a particle, multi-particle state. The idea was that, we are going to ask when that breaks down. Under normal circumstances, you would like the concept of particle to be Lorentz invariant. If I say I have an one particle state, the other guy should also agree it is an one particle state. He should not say it is a 7-8 particle state. Similarly, a vacuum state should be a vacuum state for everything. And that is what will break down because of this. The B particles vacuum state, the B particle vacuum state will contain A particles. It will not contain B particle and vice versa. Okay? So this criterion takes care of it. And that is why normal field theory books don't even mention it. Until you introduce gravity and other complications, this is a perfectly valid criteria because you work within Lorentz group structure. So the Lorentz, if you want a theory which is just Lorentz invariant, there is absolutely no problem. Now I want to go further and ask when this really creates a problem or when it becomes really interesting. So for that you have to go beyond Lorentz transformation. So what happens is that we can ask, suppose I want to construct a theory which is generally covariant. We did discuss that. We said that what you essentially need to do is to replace eta ik by the metric gik and the d4x by d4x into root g. Okay, this is how you would have constructed it in an external gravitational field. Now suppose there is an external gravitational field, then you are no longer talking about free field theory. And after all, if the external gravitational field has time dependence, then just like an external source j of x can produce particles, this can produce particles. So the concept of in, out, vacua, etc. all kick in, and you don't expect any of this to happen. The question arises as to, are there external gravitational fields in which you can introduce this kind of a mode with respect to a different time coordinate. In particular, suppose you are in flat space-time, no gravitational field, nothing physically different is going on. but I just change my coordinate system. I start with a set of coordinate t, x, y, z, and I go to another set of coordinate system. Can it happen that the new Hamiltonian allows modes which are separable like this with respect to a new time mode? So I want to give you one example of that, which is extremely intriguing, and ask what happens there. And there is a very elegant path integral derivation that when you do that, the ground state wave functional which you have here will look like a thermal density matrix in that frame with a temperature which is proportional to a parameter in that problem. So that is what I want to obtain. So in order to do that, I want to start from the flat space time and introduce a new set of coordinates. Okay. So let us start with x, which is our standard flat space time coordinate, and let me write it as psi, let us say coset g tau, and t as psi sin h g tau. So what I have done is to take x and t, and I have changed it into a set of two new coordinates psi and tau. My psi is like a new space coordinate and tau is like a new time coordinate. Okay. Now before you get lost as to what kind of strange thing this is, let us look at this thing in the Euclidean sector. Because it turns out to be a lot nicer in the Euclidean sector, and y and z goes for a ride, so I won't even mention it. In the Euclidean sector, x is same as x, this is psi, and this will be cos g tau Euclidean. That is, I am going from t to it and tau to I tau, and this will become t Euclidean, will become xi sin g tau Euclidean. Okay, because sin h will pick up an I, but this will also have an I. Cos h will not pick up an I, and it will go. Now this is something which everybody knows. This is just polar coordinates. You are starting with an x and y, because remember that t is the y axis. So you have an x and a y, and I am saying r cos theta and r sin theta. G tau is like theta. Okay. So what are we doing here? So let us try to draw this picture. If I have been working in the Minkowski coordinates, so this is t and this is x, then these transformations, what do they represent? Suppose I want to look at psi is equal to constant lines. That is given by, if I take x square minus t square, I get psi square, because cos h square minus, so x square minus t square equals constant, or the psi is equal to constant line. So they correspond to hyperbolas like that. This would be psi is equal to constant. Set of hyperbolas. Now suppose I want tau is equal to constant line. Tau is equal to constant you can obtain by taking a ratio. So if I take a t by x, it will be sin h of theta upon cos h of theta, which is tan h of theta. So tau is equal to constant corresponds to t by x equals constant. These are straight lines through the origin. So you can have a line like this. This would correspond to tau is equal to constant. In particular, the t is equal to 0 prime is mapped to tau is equal to 0 prime. Then if you look at it, something intriguing happens. Because x by t or t by x is tan h, and tan h goes from -1 to +1 as you increase. This line here actually also corresponds to tau is equal to -infinity, and this line corresponds to tau is equal to +infinity. Okay, so the time evolution goes like these parallel lines starting from here and rotating up to this. As far as space is concerned, you have this xi, and the xi is equal to 0 will correspond here, and large psi will go here. So these coordinates completely cover this region of the space time. Okay. Now you can flip the sign of psi and obtain a coordinate system which covers here. And that is just a mathematical system that will take care of this part. There are ways of putting coordinates on top and the bottom which we don't need, because we will be concentrating on the t is equal to 0 plane most of the time, so it is alright. Okay? So this is the coordinate system which we have. This is the new set of coordinates which we are introducing in the flat space. How does it look in polar coordinate? Then it is a little bit more intriguing. If you look at the same thing in Euclidean, this is TE and this is and this is just polar coordinate, so I might as well draw this and say that this is G tau and this is psi. Right? So when you work in the polar coordinate, you just work between the 0 and 2 pi. So that means your G tau E is limited to this extent, because if you do multiple copies, they will just go into each other. Now you find something very peculiar here. If I go from the real time to Euclidean time, nothing funny happens if I use t and te. T goes from minus infinity to plus infinity, t also goes from minus infinity to plus infinity. But suppose I had originally introduced these coordinates, tau and psi, in the flat space time, and then I say that I am going to go Euclidean in the new time coordinate tau, then that time coordinate becomes periodic. Long back I told you that if imaginary time coordinate becomes periodic, there is a finite temperature associated with it, and the period of that will give you the temperature. Okay, the period will give you beta, inverse of that will give you temperature. So you expect something like a temperature of G over 2 pi arising out of this, and that is what we will see. Okay. Fine. But before we get to that, let us connect it up with what we were doing here. So once you have this, you want to write down the metric, because you want to do quantum field theory in these coordinates. So the original metric is of course dt square minus the special quantity, and you can write dx as in terms of d psi and d tau, and dt as d psi and d tau, then work the whole thing out. But you don't have to do any of this, because you know that these are just polar coordinates. So it is essentially going to be g square x square, g square psi square, d tau square minus d psi square minus the two transverse coordinates in this, which is dy square and dz square. They go for that. We are only fooling around in the xt plane. What is this? This is just your dr square plus r square d theta square. G tau together you think of as theta, because it is g tau here, which is like sine theta. Okay? So in the Euclidean space, the same thing becomes, you have dt e square. So let me look at minus ds square in the Euclidean space. That will be dt e square plus dx square. That will become g square, or let me write it more properly as psi square d g tau e the whole square plus d psi square plus dy square plus dz square. I won't even write this hereafter. So this is just dr square plus r square d theta square. Okay? So this is what we have, because it's just plain sheet of paper in which we have introduced polar coordinates, and you are going to get some fantastic effect out of it, which is very strange. Okay? Fine. Now we go back and ask, how do I construct my ground state, first excited state, and all sorts of things. So for that we have to solve the Klein-Gordon equation in this metric. You can actually write down and do that. In 1 plus 1 it is trivial. But if you do it in 3 plus 1, you will get some Hankel functions instead of e to the ik dot x. But you don't even need any of that. I mean, when you do this, the main point to notice is that this metric which is written down here is static. Nothing in this metric depends on tau. Therefore, the metric is independent of tau. So when you write the wave equation, if something is independent of tau, you can expand it out as e to the minus I omega tau. Right? Therefore, you have solutions for phi, which will go as e to the minus I omega tau times some function f omega of the spatial coordinates. But if I have been working with this, I end up getting solutions like that, which goes as e to the minus I omega t times some other function which depends on the spatial coordinates. This is our standard quantization. Of course, we choose this to be e to the I k dot x, but as we were discussing, it could have been YLM beta phi, I don't care. But this was going as e to the minus I omega t. Therefore, we said these are positive frequency modes with respect to this Hamiltonian. You can have e to the minus I omega tau, which will be positive frequency modes with respect to a Hamiltonian in this coordinate system, which gives you evolution in tau. Okay, you can write down that Hamiltonian just as we wrote down the scalar field Hamiltonian for this, but it is not really necessary. But you can understand from this modes that there is going to be a different Hamiltonian here. This is what you have got.
So could you please explain the non-dependence on tau and how we...
Okay, so this particular metric, if you look at it, you can see that there is only one non-trivial metric coefficient. Everything else is 1, 1, 1. That non-trivial metric coefficient depends on psi, but it does not depend on tau. So the metric is independent of tau. So if you write down the wave equation, all the parameters in the wave equation will be independent of tau. So there will be a d square by d tau square in the wave equation, for which I can put e to the minus I omega tau.
But the d tau square, when we talk,
Yeah.
the differential element is depending on tau.
That is, yeah, but that is d square by dt square also depends on tau. That differential element is what is solved by taking e to the minus I omega t or e to the minus I omega tau. What I am saying is that, how do you get this e to the minus I omega t in flat space time? In the wave operator, you have a d square by dt square. Similarly, in the tau coordinate, there is a d square by d tau square. So you will get a e to the minus I omega tau. Okay? Rest of it I can't say anything without looking at the structure in detail, but I only need this for my purpose. Fine. Now you can already see there is a trouble brewing because your tau and t is a horribly complicated combination of each other. Suppose you have been looking at Lorentz transformation, then it would have been linear functions, but it is not. Therefore, if I take this e to the minus I omega t like this, take these mode functions. Now, these are complete set of mode functions. This with e to the I k dot x are complete set of mode functions. So any function can be expanded in terms of that. So I could have gone and expanded this. But if you expand it, this will not be pure positive frequency mode functions of this, but this will be a linear combination of this and e to the plus I omega t. Okay. So you will end up getting something very similar to this. Your one set of mode functions would be a linear combination of mode functions which involve positive frequency and negative frequency. This is exactly what we found here. These mode functions, which we wrote down here, are alpha times positive frequency plus beta star times negative frequency. This is exactly what will happen in a more complicated way. Beta will not be 0, therefore you are going to end up getting something funny. Now the only question is, why does it look like a thermal state? So in order to do that, I can do this whole thing mathematically, but there is a nice physical meaning which you can associate with this coordinate system. It turns out that this coordinate system is the natural coordinate system for observers who are moving with uniform acceleration. So in order to see that, I'm not going to work that out, you might have done it in special relativity, otherwise you should just do this. Look at, normally when you think of observers with x, y, z equals constant in an inertial frame, these are observers who are sitting quietly and they will be going up like this. Okay, they don't move and they are at the same point. Now suppose in this frame, You take observers who are at psi equals y, psi equals constant, y equals constant, z equals constant. In particular, let us look at psi is equal to constant observers. They are hyperbolas in your original spacetime. Now it turns out that if you write down the equation of motion for an observer or a particle, which is v into 1 minus v square d by dt. This is the momentum. If I multiply by m, it is the momentum. So dp by dt, which is the force, and if the force is constant, or rather this is a constant acceleration, equal to g. The dv by dt equal g would be a uniform accelerated motion in non-relativistic mechanics. In relativistic mechanics, you need to put this in. You can solve this. I will let you handle that. You can integrate with respect to t, find v, and then do one more integration, etc. And then you can also find what is the proper time of a clock which is moving along this trajectory. If you use both of them, you will find that this particular trajectory, the coordinate transformation which I have written down, this is a coordinate transformation. But if I think of psi as some constant value, then the trajectory is just x is equal to cos gt and t is equal to sin gt. And that would correspond to a uniformly accelerated observer with the same g as the acceleration. So this g has the identification as an acceleration of a uniformly accelerated observer, or proportional to that. Tau has the identification as the proper time of the clock carried by such a uniformly accelerated observer. So this entire coordinate system has the meaning as the coordinate system which is suited for a uniformly accelerated observer. So we are talking about just like you have one frame and another frame which is moving with uniform velocity with respect to it, and then you say whether the particle in one frame is the same as the particle in the other frame. And we know that if since the theory is Lorentz invariant, these are the same and the particles are the same. We are now asking a more general question. I have one frame and I have a vacuum state defined, and then I have another observer who is not in uniform velocity but they are in uniform acceleration. Is the vacuum state going to be the same for both? Is the vacuum state going to look like the vacuum state in the other frame or not? This is what we are going to ask. So what we will find when we do this is that the vacuum state which we have been working with will look like a thermal state for this observer. Okay, so I want to obtain that result next. Now there are many ways of doing this. So I am going to use a rather abstract but very powerful method. So you can get lost in the abstraction, but I think it is well worth learning, which again uses path integrals. Okay, and then I will tell you how you can do it in a more roundabout way. Okay, so let us go back to a result which we obtained very long back, which was that if I look at this is non-relativistic quantum mechanics, not even field theory. So we had this result that if I look at the path integral kernel K, which is written as integral over dq, the sum over paths of exponential I times the action with the boundary conditions, say T2, Q2, starting from T1, Q1. This path integral kernel, which we have done, had an expansion in terms of the mode functions, which we said was sum over n phi n of Q2 phi n star of Q1 e to the minus I E n T2 minus T1. This is something which we found long back, the Feynman-Cat formula. Okay. Now what we wanted, this is also something else which we did, but I want to do it in a slightly different way. Let us arrange matters in such a way that there is a nice Hamiltonian and the ground state has zero energy. That is, you shift the Hamiltonian. So previously we wanted to obtain the ground state, so now I want to eliminate that phase. So let us assume that the ground state has zero energy. Then let us go Euclidean on the time coordinate. If I do that, the same result will look like integral dq e to the minus the Euclidean action between, let us say, t2, now it is Euclidean time, q2, t1 Euclidean, q1. This is equal to summation over n phi n q2. This goes for a right, that doesn't depend on Euclidean. Phi n star q1 e to the minus I e n t2 minus t1 e. There is no, sorry, there is no I here, it is minus. Okay, that's what we have. Now I want to go one step further and I want to use a particular boundary conditions. I am going to use the boundary condition that this t1 of e is equal to 0. So let me put this as 0. And this I am going to take to be just some q. T2 of E I am going to take run to infinity. And Q2 I am going to put to 0. So since Q, first of all, since I am going from 0 to infinity, this time difference here is going to an infinitely large value. So the exponential will kill everything except the En equals 0 term. Right? So only the ground state survives. So I can just wipe this out, forget the summation and just keep the ground state. And ground state is real, so I don't need the star. Q1 I have called Q, and Q2 I have taken to be 0, so this is just a constant. And I can ignore that constant because I can always normalize the ground state. So this is proportional to phi ground state of Q. This, I have mentioned it earlier on, but this by itself is an interesting object. That is, if you want to find the ground state wave function of a system, you just have to find the Euclidean action for a particular boundary conditions and then work with that. Okay? So you have got this result, and this is, of course, this kernel can be written in terms of your standard Hamiltonians and evolutions, etc. The same thing works even in field theory. So in the field theory, it would have been, because nothing in this said how many degrees of freedom you have, you can take each one of the harmonic oscillators, work the whole thing through, and the same thing will happen. So you have the ground state wave functional of a field theory will go as, which of course depends on the field configuration, phi. Let us look at the wave functional at t is equal to 0. So this will be proportional to the path integral kernel over d phi e to the minus the Euclidean action, which is obtained with at infinite Euclidean time the field is vanishing. As t goes to infinity, the field vanishes there, and at t is equal to 0 surface, the field has this particular boundary value phi f. Okay, this is what we have. Now let us look at this. Let us stare at it a bit. What are we doing here? So we have a space-time, but in Euclidean space, this is TE, and this is X. Okay. and you are looking at an action, take this, let's just concentrate on this. What we are saying is that at x is equal, at t is equal to 0, that is here, I am assuming the field has a particular configuration, phi of x, on this whole space at t is equal to 0. Some field configuration is given for you. Then I am integrating it over this entire half space with the boundary condition that at very large distances and at very large t, the field vanishes. Okay? So I have to sum over all kinds of field configurations in this region in order to do this integral. Now there is a nicer way or a different way of doing the same integral. Instead of doing it in this Cartesian coordinate, let us do it in polar coordinates. So I introduce the polar coordinate, this is xi, and this is your g psi is theta. So if I want to integrate all over this, that is, if I am going to integrate over each time slice like this, instead of that, I can take one particular radial line, integrate the field along this, then take another radial line, integrate along it. So the integration along this d from here to here is the same as the integration along this. Therefore, I can write this as proportional to the same kind of an integral or the sum over fields of e to the minus. So I am going from here to here in time. So let us say that the field had some values here which I will call phi r, which is on the right hand side. It had a particular configuration and it had a particular combination phi n. Nothing has changed. Instead of original phi of x, which was defined everywhere, I call the part of phi of x on this side as phi r of x and this as phi l of x. So the left hand side, the ground state wave functional is now given in terms of phi l and phi r. So the psi ground state, instead of the full phi, I am going to write it as phi l and phi r. That is given by integral over d phi e to the minus the Euclidean action. So the time is now going from 0 to pi. So t is not infinity here, it is equal to g tau equals pi. So tau is equal to pi by g. And when I rotate from here to here, on this time the field is phi l. And on the 0, the field is phi l. Okay? So instead of taking this and integrating all over the path integral, I am just doing the path integral in this polar. But this I can now write in Hamiltonian form. This is nothing but the Hamiltonian evolution between phi l and phi r with e to the minus the time difference, which is pi by g, and the Hamiltonian, whatever that Hamiltonian is. The intriguing thing is we don't need to know that. Okay. So the ground state wave functional has an expression where you start from the field configuration phi r here, evolve with respect to the Hamiltonian, which is producing translation in the tau coordinate, which would have given you the e to the minus I omega tau, and all the way up to this end. So this is what you have. So far there are no surprises. I mean, it's just another way of writing it. The really interesting thing happens at this stage. I now say that suppose you have an observer and all this was done, oh, I wiped out a little too much, but it doesn't matter. All this was done with the idea that in the flat space-time I have introduced these coordinate systems, and this is the way it covers it. And I am looking at t is equal to 0 situation, so this is this line. And you had field configurations phi L on this side and phi R on this side. Okay? Now suppose there is an observer who only cares about observations in this region. For example, if you have these uniformly accelerated observers, they are never going to pick up anything from this side. Even if he was starting with some constant velocity and going like this, none of them can get any signals from beyond this side. That is, this line acts as a horizon to these observers. The signal sent from here will only go like this. And in quantum mechanics, we have worked out the commutation rules between the phi L's for space-like separation, etc. So the same thing carries on. So an observer who is constructing an observable based on just phi R might want to compute its expectation value in the ground state. So what he will do is that he has some observable which is built out of phi R, and he wants to compute its expectation value. So he will have to take the ground state wave functions and multiply and all that. But essentially what it will involve is to having two of these objects and then taking the trace. That is, he is going to integrate out everything on the left hand side. So let me just write that down. So what he will have is an okay. Here is the observable which depends only on phi R. Then I will have two copies of that ground state multiplying it. So the two copies of the ground state will be phi R e to the minus pi over g h phi L, phi L e to the minus pi over g h phi R. So I am taking this and take one more copy of that because I have to take mod square. Mod is not relevant here, but when you take the mod, the phi R and phi L will flip. So that is all I have done. So you have one with a phi R and phi L, which is what you have there. Then the other with a phi L and phi R. This is how Hermitian and real and whatnot. So you have this. Then you have this. And you are summing over all field configuration phi R and phi L. Okay? Now, first of all, when you sum over all phi L, that is trivial. So you are just summing over this complete set of states here. So this just goes away. And these two things will combine. So you end up getting e to the minus 2 pi over g times the Hamiltonian phi R. Okay. This is exactly what you would have got if you had written it as proportional to. This is also proportional to because the wave functions are only proportional to. If you have written it as trace e to the minus 2 pi over g h times this operator, where this quantity comes in as the density matrix. Okay, because we are only taking the diagonal elements of that and summing over this. What is this density matrix? The density matrix which you have got, rho of phi r prime phi r, is just phi of r prime e to the minus 2 pi over g h phi r. But this is just the thermal density matrix. But this is e to the minus beta times h. And the beta you can read off. So this corresponds to a temperature which is G over 2 pi. This is almost like a magical derivation. This is originally due to TDD, the Nobel laureate. So he came up with this way of doing this. The advantage of this derivation is that we only assume there is a ground state and the Hamiltonian is bounded from below. It can be made to 0. We never said it's a free field theory. Okay. I never had to say what this action is. So even if you have a complicated field theory with all kinds of interactions, you have the result that if it has a nice vacuum state and you look at the vacuum state from an accelerated frame, it will look like a thermal state with a temperature which is G/2. If you go through this, as I said, up to this point there are no surprises. It is just rewriting the ground state wave functional in a different way. And this could have been done in a much more nitty-gritty way. So let me just explain to you what that nitty-gritty way is. If you look at the ground state wave functional on this t is equal to 0 surface, that will have a product of factors like exponential minus half omega k mod qk square. Where qk's are our old friends, our normal harmonic oscillator modes which comes from the phi. But what you can do is that you can write this qk. See, the qk is obtained by integrating, let me do it in one dimension. So integrating over dx of phi of x at t is equal to 0. E to the, in our notation, it should be e to the plus, no, e to the minus ikx. Okay, this is kx, x component times x, this is the x coordinate. Now what you do is you separate this out into two integrals. You write it as an integral from minus infinity to 0 plus an integral from 0 to infinity. In 0 to infinity, you introduce a new coordinate system. So you can write all these things in terms of the new coordinate variables. In the minus infinity plus infinity, you introduce another coordinate system with a minus sign. Then the phi at either of them, you write in terms of the corresponding harmonic oscillators here and here, which I can call AK and BK. So if you do that, it is obvious that this will turn out to be proportional to some linear combination, some alpha AK plus some beta BK. So what is involved, I mean actually it will be like a matrix, but that doesn't matter. So your QK mod square can be written in terms of a linear combinations of AKs and BKs. That will have a cross term, AK BK. So your original ground state wave functional will now be not made out of a whole lot of harmonic oscillators which do not see each other. Here the ground state wave functional is a product wave functional. So every QK is independent. But the moment you write in terms of this, the modes here and the modes here talk to each other. This is called quantum entanglement, which is an extremely important concept by itself, but we don't have time to go into that. So the modes do talk to each other. Now if you integrate out all the BK modes, say on the left, then you can construct a density matrix out of this wave function. That is, you start with a ground state wave functional and convert it into a wave functional which depends on set of modes, BK on the left, let us say, and AK on the right. Then if you take psi star and you integrate out the left modes BK, you will end up getting a density matrix in terms of AK and AK prime. Okay? And that density matrix you can show is identical in structure to a thermal density matrix, and that has this form. It turns out that this is doable, but it is enormously complicated mathematically because you need to do integrals over some gamma functions and things like that. The whole thing can be completed, and finally you end up getting the thermal density matrix. But this derivation is a lot easier and lot more elegant. And here, of course, you have to assume that these are the ground state wave functions. which means that you are assuming it is a free field theory. Okay, it doesn't work. I mean, if you want to work with a more general field theory, it is not possible. So this is, as I said, this is just magical that without making any of those assumptions, you can apply this result. But it tells you that it comes about because there are certain degrees of freedom which you have integrated about. But from our point of view, we want to think of it as coming about because your mode functions have changed. You started with mode functions which are e to the minus I omega t. And then in the other frame, that other fellow was using mode functions which went as e to the minus I omega tau. And these mode functions are linear superpositions of the original positive and negative frequency. Therefore, if you, okay, I have given you here just the density matrix. Now, one of the operators you may want to construct is a number operator here, which is AK dagger AK. I didn't work it out, but this is a standard exercise in statistical mechanics. That if I have AK dagger AK and you calculate its expectation value with the thermal density matrix, you will get a Planck spectrum. So what he will find is that if I have a theory in which there are certain excitations with an energy omega, then the number of particles in the inertial vacuum, that is the way the terminology is used, the standard vacuum state from our phi field in inertial coordinate system is called the inertial vacuum. The vacuum state corresponding to this accelerated observer is called either non-inertial vacuum or Rindler vacuum, because this particular transformation goes under the name Rindler transformation. So the Rindler observer will see a thermal distribution of particles in the ground state. So what we have written down as a ground state wave function is going to look like a thermal density matrix corresponding to a temperature depending on the acceleration. So the first thing it tells you is that the concept of particle is Lorentz invariant, but it is not generally covariant. The moment you introduce non-inertial frames, you can no longer talk in terms of particles. That is vacuum state, one particle state, two particle state, etc. You have to say which observer you are talking about before you do that. This is in some sense like energy and momentum or time and space. In Newtonian theory, time is absolute. If you say that my time coordinate is t and I am talking about t is equal to 15 seconds, you don't have to say which observer. But the moment you go to special relativity, if you say my time coordinate is 15 seconds, then you need to know which observer you are talking about. Two Lorentz observers do not agree on that specification. So in the same sort of way, in Lorentz invariant theories, if I say I am looking at a 13 particle state, you don't have to say which Lorentz observer. All of them will agree on the 13 particles. Their momenta will differ, but they will still count the 13 number of particles. But the moment you go to a generally covariant theory, you have to say with respect to which observer you are talking.
Sir,
Yeah.
sir, how can you see that it's not generally covariant?
The concept of particle is not generally covariant, because if I go from one frame which is an inertial frame to a non-inertial frame, general covariance says that the physics as described by one frame, the inertial frame, all inertial frames have the same physics in normal Lorentz invariant theory. In a generally covariant theory, all frames should have the same physical effects. So for example, if I have a concept of a vacuum state, when I make a Lorentz transformation, the vacuum remains the vacuum. But if I introduce these coordinate systems, which are not Lorentz transform coordinate system, but a general coordinate transformation, then we have explicitly found that the vacuum doesn't look like a vacuum. So it is in that sense that the vacuum is not generally covariant. Okay? Yeah, so this is probably a good place to stop. And those of you who are interested can try this out. This is, as I said, it's messy, but it can be done, and it's a good exercise. Okay, and next lecture I will do complex field and probably just introduce the electromagnetic field, and then we will proceed further. Does any of you Pune University student have a Viva on the week after that? A Viva or project Viva or whatever? You said they don't know it or whatever, right?
Yes, but I'm not aware of the specific dates that we are supposed to be doing.
Okay, so when will you know?
I guess after 10.
Okay, so you let me know and then we will keep in touch. So